Hello, welcome to the special limits. Today I will discuss the special limits number 3, 4, and 5, and I will also exactly prove them. The title of the lecture is Why Only Those Are the 5 Special Limits of the Classical Calculus, those 5. I will answer this question why at the end of the lecture and also as I go. As you remember, the special limit number 1, I proved it. Limit of sine x over x when x goes to 0 is equal to 1. This is 0 over 0 indeterminate form, and all other trig limits are exactly derived, are reducible to this limit, such as limit sine ax over x, a is a constant. Every calculus book has this proof. Ax is equal to a new variable y, let's say, and you can easily prove it. The limit tangent x over x goes to 0. Arc sine x over x, arc tangent x over x. All of those are reducible to the special limit number 1. Even the limit of 1 minus cos sine x over x when x goes to 0 is equal to 0. This is not a special limit. There are so many YouTube postings where people say that this is special limit. No, this is not a special limit. This is just a trig limit. There is nothing special about this limit because it is exactly reducible. It is derived from the special limit number 1 first, and second, that's the same nature of the function. That is the nature of the trig function. There is nothing new in this limit. So this is just a trig limit. Versa, all of those 5 limits, they represent different groups of elementary functions, all elementary functions in the classical calculus. The limit number 2, the limit of 1 plus 1 over x, x goes to infinity, power x, equal to limit of 1 plus x, as goes to 0, power 1 over x, is equal to e. That is an irrational constant, which is equal to 2.7, followed by the year of birth of Leo Tolstoy. Leo Tolstoy's birth year, which is 1828, 2 times. 1828, 1828, 459, and so on. This is called the Euler's number, not the Euler's constant, because the Euler's constant is another value. This is called the Euler's number, which is an irrational constant. So what's special about second limit? That's the discovery of this magical super important number e. That's different nature. That's not a trig nature. The special limit number 3, very easy to prove it. It's a new limit of log of 1 plus x base a over x when x goes to 0. That's 0 over 0 indeterminate form. It's equal to log of e base a, or it's equal to ln a power minus 1. That's the same value. You know, that's the basic property of logarithms. That's the change of the base formula for the logs. Just use it, and you can use either one of those values. The special limit number 2, that is 1 to the infinity indeterminate form. When you have limits of this indeterminate form, you always reduce them to the special limit number 2, and this will help you to resolve them. So how to prove the special limit number 3? Super easy, just one step. It's equal to, using the basic property of the logs, 1 over x factor, you can bring it under the log as the power of the function under the log. So 1 over x was here, bring it here as the power 1 over x when x goes to 0. And now you have exactly what? You reduced it to the previous, the special limit number 2. The function under the log approaches to e, according to special number 2. So finally, the result will be log of e base a. That's the end of the proof. Very simple. And you may ask me, why this is special limit? Yeah, I also derived it from the previous one, the limit number 2. Why? Because this limit gives us the nature of the log functions. That's the group of the elementary functions. And moreover, it helps us to calculate the derivatives of the log functions. This is exactly the structure of the limit of the difference ratio for the derivatives, as you remember, the limit of the difference ratio for the log functions. So one is fixed, infinitely small value x contracting, divided by the same infinitely small contracting value of x. You fix the value here, and that's the log function. And exactly, it helps us to calculate the derivative. Again, there are not many groups of elementary functions in the classical calculus, only like trig functions, especially number 1, the log functions, number 3, the exponential functions, number 4, and the polynomial, the power functions, number 5. And that's it. This is practically it. That's all the groups of elementary functions in the classical calculus. Even the hyperbolic trig functions, they all are derived from the exponential functions. So that's not really a new group of the elementary functions. Again, that's why only those are 5 special limits, because they cover all the groups of elementary functions of the classical calculus, and they exactly help us to calculate their derivatives, which is super important for the classical calculus. So the special limit number 4, that's the limit of a to the power of x as a constant minus 1 divided by x when x goes to 0 is equal to ln a. A is not equal to 1, a is positive more than 0. That's the domain of the log functions. Please remember that. Many people forget this, and they have problems when solving the log equations and inequalities. Very easy to prove it. This is actually the nature of the exponential functions here. We'll prove it by introducing a new variable. When we introduce a new variable, we use a keyword let. Let's say let a new variable y is equal to ax minus 1. So I'm switching to a new variable y. So when x goes to 0, y also goes to 0. The dynamics of y is easy to see. X goes to 0, constant a, non-zero constant a. To 0 is 1 minus 1, 0. So from here, y plus 1 is equal to a to the x, which means that my x is equal to log of y plus 1 value base a. That is my switch, my new transformation between the variables. So from here we can say that this limit is equal to ax minus 1, that is my y. This is how I introduced a new variable. So it's equal to y over x. And my x in the terms of y is log of y plus 1 base a. Y goes to 0. So I switch to the y variable now. So you can see I'm trying to reduce it to the previous established special limit, and it's equal to the limit of 1 over, I can write as a multi-level fraction, log of y plus 1 base a over y, y goes to 0. Look at this, right? Multi-level fraction. Look at the fraction in the denominator. That's exactly reducible to the special limit number 3, which is equal to ln of base a power minus 1. So this goes to ln a minus 1. That's the number 3, the special limit number 3. And since that's the reciprocal 1 over that, it's finally equal to ln of a. QED, that's the end of the proof number 4. We just easily proved number 4. The limit of ax minus 1 over x as goes to 0 is equal to ln a. And again, when you prove something, you try to reduce it, derive it from the previously established axioms, theorems, facts, and statements. This is how we prove everything in math. Next group of next special limit, the last one, so the special limit number 5, which covers the group of polynomial, the power functions. That's another group of elementary functions, and that's actually it. And the limit 1 plus x power alpha in general is a real constant, minus 1 over x, x goes to 0, is equal to this constant alpha. This is 0 over 0 in determinant form. There are many sources where they prove this limit using the binomial extension. That's correct, but the binomial extension works only for the natural powers, and you can extend it for the rational powers. What if you have irrational power, the real number in general? Then the binomial won't help here usually. That's why I will prove it not using a binomial. I will prove it in two ways. Let's say I will prove it by introducing a new variable, and way number 2, I will prove it by introducing a new function. So let's look at the way number 1. Way 1, let's say, let my new variable y is equal to 1 plus x power alpha minus 1. So this is my new variable y. I'll just introduce it this way. Then y plus 1 is equal to 1 plus x power alpha. How do I bring alpha down? By taking logarithms of both parts. You know that basic property of the logs, which means that ln of y plus 1 is equal to alpha ln 1 plus x. And this is my transformation. Now let's look at the dynamics. So when x goes to 0, my y also goes to 0. It's easy to see that. X goes to 0, so I have 1 alpha constant, 1 minus 1 is 0. Y goes to 0. So according to this transformation, my, let's say, way 1 proof will look like this. That's a proof. Proof way 1. So my limit 5 will be equal to the limit of y over. My numerator is exactly y, yeah, by using this transformation. It's y, yeah? Y over x. The denominator is x. Both variables go to 0. Y over x is equal to 0. Now next step, I will multiply both by ln y plus 1. By ln y plus 1. The value is preserved. It will ask me why. Math is like playing chess. When you do something, when you make a move, you need to predict the outcome of that. You need to see what will happen as the result of your move. So in this case, when I multiply by ln y plus 1, I'm trying to reduce it to the previously proved established special limit number, let's say 3 in this case. So it's equal to the limit. I can write this way, y over ln y plus 1 separated. Two fractions, x is here, and the ln in the numerator on top, y plus 1, I will substitute its value in the variable of x, because here of x variable, right? So which is equal to alpha ln 1 plus x. Both go to 0, x and y, both variables go to 0. And look at this, what we have here. That's exactly the special limit number 3. It's just the reciprocal of that. So you can use the same strategy I used here, multi-level fraction. I can write as 1 over ln y plus 1 over y, exactly the same here. And my denominator fraction will approach to ln of e, log of e base a. My base is e, ln of e, log of e base e, which is ln e. So this is actually the reciprocal. So 1 over ln y plus 1 over y. So this will be actually the reciprocal 1 over ln e, which is 1. That's 1. So it approaches to 1, which is number 3. This whole thing goes to 1, and the second fraction exactly goes to ln e, which is also 1. It's also number 3. All of those approach to 1. What's left? My alpha is left here. Alpha pops out here as the constant. So that's the end of the proof. Finally, number 5 proved. You can see it's equal to this real constant alpha. I proved it by reducing it to the special limit number 3. Way number 2, proof. Way number 2. So I will introduce a new function now. So let me do this. Let 1 plus x power alpha is equal to e to the t. Those are two continuous functions, the power polynomial and the exponential function. I can equate them this way in this case. Different variables. Since 1x alpha is equal to e to the t, then so I'll try to switch to x. I'm trying to switch to x variable. Or e to the power t over alpha minus 1 will be equal to x, yeah? So that's my x variable now. So from this, I can write my 5 will be equal to the limit 1x alpha, that's e to the t, that's e to the t minus 1 over x. My x is, I can separate them this way, x is e t over alpha minus 1. That is my x. Now, look at this. I'm trying to reduce it to the special number 4, kind of exponential nature, which says e to the power of variable minus 1 divided by the same variable, which is t, x. So that's t. So if I divide it by t, will look exactly as the special number 4. But t was not there, so I need to compensate it by multiplying by this variable t. So I can separate fractions this way. So let's say I will multiply it by, divide and multiply by t. Nothing's changed, everything's the same. I'm switching to a new variable now, to variable t, which also goes to 0. We can say that when, actually we need to mention that when x goes to 0, my t also goes to 0. It's easy to see that. When x goes to 0, so 1 plus 0, 1, alpha constant, and it's 1, so e to the 0 will give me 1. So t goes to 0. So first fraction is exactly number 4. The special limit number 4, and it approaches to ln a. My a base is e. So ln e, which is 1. Ln e, it's 1. Next fraction, also very close, e to the power minus 1 divided by the same power, which is t over alpha. Alpha was not there, so I need to compensate it by multiplying by the same alpha. And here I have special number 4, just the reciprocal of that fraction. I can do the same thing I did here, 1 of multi-level fraction, so 1 over e t alpha minus 1 over t alpha. So 1 over, in the denominator will be ln e, which is on 1 over on 1. So it also goes to 1. 1 by alpha, finally it's alpha. So it's QED number 5. As you can see, I just proved the special number 5. And again, only those are the special limits because they help us to calculate exactly the limits of the difference ratios for all of the groups of elementary functions. The trig functions, the log functions, the exponential, and the power polynomial function. And that's all. That's it. That's all the elementary functions known in the classical calculus. That's why they're called the special 5 limits. And again, this limit is no way special limit. It's just a trig limit, which is derived from the special number 1. There is nothing new in that limit. Now, couple of remarks. Let's say remark number 1. Some slight modification of the limit number 2. Modify number 2. Slight and important modification number 2. So, the limit of 1 plus n over x, power x goes to infinity. You can see it's 1 plus infinity is 1. N is a constant. Yeah. N is a fixed constant. 1 plus infinity small to the power of x. Doesn't really look exactly, but very similar. Yeah, I need to raise it to the power of the reciprocal on that. So this is what I will try to derive from here. X goes to infinity. 1 plus n of x, n over x. It's 1 to the power of infinity in determinant form, so I'm using the special number 2 to resolve it. Now to the power of the reciprocal, and I need to compensate that n, it was not there before, so we'll raise it to the power of n. Overall, it will be just power of x, the one I was given in the beginning. So it's equal to what's inside. Inside, that's exactly number e. It goes to e when x goes to infinity. It's exactly number 2. That's the special limit number 2, and the answer is e to the power of n. This is wonderful observation. Why? Because this is very important formula. I guarantee this is your money. Your money is moving according to this formula. This is almost exactly, that's practically exactly the formula of the compounded interest rate with the given APR, the term, and the number of compounding intervals within a year. That's exactly is described by this pattern, by this formula. So the limit n constant over x, power of x to infinity is equal to just e to this power of n. Very important, the banking system is using this formula. Remark number 2. I'll modify also practical application, modify number 4. Number 4, especially number 4, let's say if my x is equal to 1 over n, where n is a natural number, if my x variable is equal to that for the number 4, then I have the limit of ax minus 1 over x. When x goes to 0, now I'm switching to the n variable, new variable n. It will be equal to the limit. X is 1 over n, so a power 1 over n, that's the nth root of a. So that's the nth root of a minus 1, and everything is divided by x, which is 1 over n. N goes on top, so it will be a factor of that expression. And now I have new variable n. Now my n goes to infinity. Yeah. So when x goes to 0, my n goes to infinity, and it's equal to ln a. This is very also useful limit. It has 0 by infinity or infinity by 0 indeterminate form. So whenever you have this kind of indeterminate form, this is one of the ways to resolve that indeterminate form. That's also very useful application of the special limit number 4. I hope that was clear. And again, let me summarize. There are only 5 special limits given here. They represent all the groups of elementary functions of the classical calculus. The group of trig functions, the group of log functions, the group of exponential functions, and the group of polynomial power functions. And that's all. That's all the elementary functions known. The gamma functions, the beta functions, the integral sine, integral cosine, the Bessel's functions of the first kind, of the second kind, those are not elementary functions. They are non-elementary functions. The elementary functions given here by those 5 limits, and moreover, the limits number 3, 4, and 5, they help us exactly to calculate directly the derivatives of all of those groups of elementary functions. They exactly represent the limits of the difference ratios of those groups of elementary functions. When you calculate the derivative of the exponential function, you'll be solving that limit of the difference ratio, you'll be modifying it, and you'll come exactly to this form to resolve that limit. When you find the derivative of the polynomial power functions directly, you look at the limit of the difference ratio, and will come exactly to this form, and you'll be able to calculate that limit, to calculate the derivative directly for the polynomial. The same thing for trig functions, and that's practical. Number 2, it's a special limit which discovers this magical number e. I hope that was informative, interesting, and I will see you soon where I'll be solving exactly problems with those 5 special limits. Thank you very much for your time. See you soon. Bye-bye.